This is section 2.3, and what we're going to be going over is the limit laws. So let's jump right in. To begin with in this section, what we want to do is construct two different kinds of limit laws. The first is we're going to find some limits of some basic functions, and then we're going to look at how to combine limits together using our normal operations and see how that works with limits. So we're going to begin with two simple functions, the constant function f of x just equals a constant, and the identity function f of x equals x. So let's look at what these look like on a graph. So here's f of x equals 3. We have our graph of a line y equals 3. And if I think about what happens as I get near an x value, let's suppose that we pick an x value of 2 here. As my x values get closer and closer to 2, the y values are always 3. So it doesn't really matter where the x values are going, the y values are always 3. So if I'm approaching 2, the y values are approaching 3. If I'm approaching an arbitrary x value a, the y values are still approaching 3. So what we get is that the limit as x approaches a of f of x is 3. If I take a different constant, right, if I picked f of x equals some different number, I would have the same pattern. So what we can do is come up with this general idea, this general limit. If my constant is c, as x approaches a, the y values are going to approach c. So I get this limit as x approaches a of the constant c is just c. Okay, let's look at the identity function x. Here, y equals x. And since the y value is always equal to the x value, suppose I'm approaching the x value of 2. As my x values get closer and closer to 2, right, I'm going to have these points on the graph getting closer and closer to x equals 2. But since x equals y, if x is getting close to 2, y is also getting close to 2. And there's nothing special about 2, so we can generalize again. As x approaches a, the y values are also going to approach a. So the limit as x approaches a of this function f of x is a. Okay. Or just like last time, we could write that as the limit as x approaches a of x equals a. Okay, now the constant function and the identity function on their own are not super important functions that we see all the time. What we're going to do is look at how can I combine things together. So I'm really going to just use these as building blocks. So let's look at how we can combine things together. So suppose that we have two functions, f of x and g of x. If I take the limit of these two functions added together, right, if I look at this first limit law, then I'm just going to think of that as being the limit of the first one plus the limit of the second. So another way to look at that, if I'm looking at a function that is two functions added, and I'm saying what happens as x approaches a value, I can look at what happens as x approaches a value for the first function and the second function separately and then add them together. Because since I'm adding anyway, it doesn't matter if I do that before or after I look at what happens, as I approach the function. Okay. And it turns out that I can do this for like all of my normal math operations, right? If I'm multiplying by a constant, suppose I have some function and I'm multiplying by 5. It doesn't matter if I multiply by 5 before or after I do my little approach pattern thing. I'm going to get the same result. Okay? Or even if I multiply two functions together. One place where things get a little bit wonky is with dividing, and it's only when we divide by 0. If I get a 0 in the denominator, with a limit, because I ignore what happens exactly at A, we might still get a result that would be different than if our limit is 0. Okay, and we'll look at some examples of that. So this is the one that we need to be careful about. Okay, and if I take a power outside a function, right, that's the same as if I do that in or outside of the limit. So let's go ahead and look at these limit laws. Now, normally in math, I think you're probably used to when your teacher gives you a theorem, they give you some explanation about why it's true, or maybe even a full proof. And here I've given you very little. The reason for that is we can't prove this yet because we haven't actually stated exactly what a limit is. In order to prove something is true for a limit, you need to know what a limit is. And the precise definition of limit is the last section in this chapter. And that seems backwards, but that's just because limits are a very difficult concept to write down precisely. So we're kind of doing things backwards because it's easier to learn that way. All right, let's look at how we can actually apply the limit laws. So here's an example. I want to use the limit laws to evaluate this function. Okay. What I'm going to do is I'm going to think of this function as being these pieces all added and subtracted separately. So we're going to use that first limit law to say that this is equal to the limit as x approaches 3 of 4x squared minus the limit as x approaches 3 of 3x plus the limit as x approaches 3 of 7. Okay, and now we're going to use law 2 to pull the constants out, right? So I didn't number these back here, but we'll just refer back. If I have a constant times a function, I can factor that constant out. So I can write this as 4 times the limit as x approaches 3 of x squared minus 3 times the limit as x approaches 3 of x plus the limit as x approaches 3 of 7. Okay. Now I'm going to go ahead and use, I suppose if I was counting, this would be number 5, the limit law that has to do with powers. So I can write that as 4 times the limit as x approaches 3 of x, that is then squared. And that's a minor difference between the rule before it, but this now leaves me with only limits of the function x and limits of a constant. So I'm going to go back now to these two functions that we figured out. The limit of a constant is that constant, and the limit as x approaches a of x is just that number a. So we're going to use the two limits we found to write this is 4 times 3 squared minus 3 times 3 plus 7. And this allows us to, easily compute what's going on as a number, but I don't even find that number really important here, right? So I'm gonna consider this part done, but I'm not going to write down what that number is, because what I want to do is focus our attention on something. What does this look like? And if I look at what I've written down here and I look back at my original function, it looks like I just plugged 3 into the function, right? If my function f of x is 4x squared minus 3x plus 7, then f of 3 is 4 times 3 squared minus 3 times 3 plus 7. So what I have written down here after applying my limit laws looks exactly like just plugging into the function. And that's not an accident. Any polynomial that I write down, when I break apart with limit laws, the same thing is going to happen. So what that does is it provides us a method for computing limits, I can just plug into the function. Okay. So that gives us a theorem, and that explanation is as much proof as I'm going to give you. Again, I'm not going to do a full proof, but what we can do now is when I want to figure out a limit, we're just going to plug into the function. And we've shown that this works for polynomials, right, based on the example we did. And we showed that this works, well, we didn't show it, but similarly it would work for a rational function if I had a fraction, as long as the denominator is not 0. Okay, because I could just apply this limit law 4 here if I had a fraction and just break limit over top over bottom, as long as the bottom's not 0. Okay, and it turns out that this is also going to work for other functions, but it takes a little bit more work to show that. Okay, so our theorem for direct substitution, in general, is going to look like the limit as x approaches a of f of x equals f of a. Okay, and as long as my function is a nice function, this will work. Okay, so let's look at an example. This is the exact same limit that we just figured out. But what I want to do is look at how would I do this with direct substitution. Okay, so what I can do is say, okay, using direct substitution, I could just say that this is equal to 4 times 3 squared minus 3 times 3 plus 7. And of course, we always want to give some explanation of what we're doing. But in this case, that's it. I've plugged in, and now I'm just working with simplifying a number, right? 4 times 9 minus 9 plus 7. Oops. Subtracted 7 instead of adding 7. So I think that comes out to 34. But the point is that now when I plug into a function, I apply this direct substitution. Okay, so let's just make a note here. We're not going to use the limit laws directly. The way that we use the limit laws is that they give us direct substitution. Okay, so don't use the limit laws directly to solve problems. Use direct substitution. All right, let's look at some examples. In this first example, what I'm going to do is try direct substitution. Okay, I'm going to say, all right, this is 2 squared minus 4 over 2 plus 2, which is 4 minus 4 over 4, which is 0 over 4, which is 0. When I did direct substitution, I didn't get a 0 in the denominator, so it's fine, so we're done. Okay, it's only when we get a 0 in the denominator that the direct substitution fails and that we have to try something else. Okay, the other thing I want to note early on here is that this is a limit. So we write the limit out front. Once we've done direct substitution, so after direct substitution, we have a number. Not a limit. So we stop writing the limit out in front. Okay, so that's just good writing habits. All right, let's look at another example. Here, I'm going to try direct substitution. Okay, and when I do that, I get negative 2 squared minus 4 over negative 2 plus 2, which is 4 minus 4 over negative 2 plus 2, which is 0 over 0. So there's two things here that I am able to tell. First of all, I have a 0 in the denominator, so I wasn't allowed to use direct substitution. Okay. The second thing is, when we end up with 0 over 0, I know that when I'm plugging into a polynomial, if I plug in a number and it gives me 0, that means the number I plugged in is a root, so x minus that number is a factor. Okay, so what I can do is I can try to factor this. So what I'm going to do is start with my limit, again, fresh. And I know that I can factor the numerator. The denominator is already as simplified as it can get, right? X plus 2 can't really be factored any further. But the numerator can be factored into x plus 2 times x minus 2, right? The difference of squares. Okay. As an expression, x plus 2 times x minus 2 over x plus 2 is not equal to x minus 2, okay, because the domains are different. What's the difference? Well, on the left, I can't plug in negative 2. In a limit, remember what we're talking about is approaching this value, but ignoring what happens exactly at that value. We're only looking about getting infinitely close. Okay? Since we're only looking at getting infinitely close to negative 2, but not actually at negative 2 itself, then I don't need to worry about that because my x values aren't allowed to be negative 2. Okay, so in my limit, this is fine and things cancel. Okay, so this is equal to the limit as x approaches negative 2, and I'll just rewrite this so that we can see the canceling without all the craziness going on. I can cancel my x plus 2 factors. And then we have the limit as x approaches negative 2 of just x minus 2. Now we can use direct substitution. I'll just abbreviate that ds. And when I use direct substitution, plugging directly in, then I get a number. So my original limit as x approaches negative 2 of x squared minus 4 over x plus 2 was equal to the second limit, which is equal to the third limit, which is equal to the fourth limit, which is equal to negative 4. So it's equal, write this down, limit as x approaches negative 2 of x squared minus 4 over x plus 2 is equal to negative 4. Okay, so that's how that direct substitution can benefit even in a situation where it doesn't work initially. Okay, if I plug in and I get a 0 in the denominator, I just have to do some more work. Okay, let's look at an example where we have a fraction inside the fraction. Okay, the way that I always want to try starting limit problems is to try direct substitution and see what happens. So I'll have 2 times 3 plus 2 over 3 minus 1. Okay, and then minus 4, and then in the denominator of my big fraction I have 3 minus 3. So let's see what happens. 2 times 3 is 6, plus 2 is 8. 3 minus 1 is 2. 8 over 2 is 4, minus 4 is 0, so I get 0 over 0. Okay, the difference is that here I get 0 over 0 just like we did in the last example. But in the last example, I just had a polynomial over polynomial, so I know that things factored. Here, I don't have a polynomial in the numerator, right? I've got this crazy fraction inside a fraction, so I can't just factor, but we can still think of this, you know, something similar is going to work. I'm going to use algebra to simplify this. But because I have a fraction inside my fraction, I can combine things together. And the way that I combine a fraction with another number is by getting common denominators. Okay. So we're going to have the limit as x approaches 3, 2x plus 2 over x minus 1. And this 4 over here, I'm just going to multiply by x minus 1 on top and bottom. Okay. Let's go ahead and distribute that. When I'm working with fractions within fractions, I'm going to show you an algebra technique that I use that keeps me from losing negatives. And I do this anytime I'm subtracting fractions. I don't actually subtract fractions. I bring the negative into the second fraction and change it to a positive. Okay. So instead of subtracting, I'm going to add a negative. The reason that this is helpful is because now when I distribute this negative 4, I'm very aware of a negative getting distributed. So now I'm adding, and I'll have negative 4x, and negative 4 times negative 1 is plus 4. A really common algebra mistake that students make is when you're subtracting fractions, the first term gets that negative on it, but the second term doesn't. And then now you have something incorrect, you've made a mistake, and it's really easy to lose that negative because you're not focusing on that. You're focusing on, okay, I'm either distributing or getting a common denominator, you know, I've got other stuff going on, and it's easy to make that little oversight. Okay, now we have the same denominator. Let's combine the numerators together. So 2x minus 4x is negative 2x. 2 plus 4 is 6. And in my denominator, I'm going to rewrite this x minus 3 as an x minus 3 over 1. Because when I divide a fraction by a fraction, I can change that into multiplication. And now we're going to be down to just one layer of fractions. So we have negative 2x plus 6 over x minus 1 times 1 over x minus 3. And I feel like that looks better right now. I just have this one layer to work with. Okay, since I want to plug a 3 in eventually with direct substitution, this x minus 3 I know is my problem piece. So I would really love to cancel it with another x minus 3 factor. So I'm going to look at this negative 2x plus 6 and say, can I factor something out? And indeed I can. If we take out a negative 2, we'll be left with an x minus 3. And now we have these x minus 3 factors that we can cancel. Again, because we're inside a limit. Okay, so now we have the limit as x approaches 3 of negative 2 over x minus 1. And now we can use direct substitution. So we'll get negative 2 over 3 minus 1. Notice that this is the step where I stopped writing my limit. I had to write the limit out front for all of these other steps because I can't do this canceling if there's no limit out front. Okay, so I get negative 1. So the limit as x approaches 3 of 2x plus 2 over x minus 1 minus 4 all over x minus 3 is equal to negative 1. Okay, let's look at another example. This one has a square root involved. The way that I start is the same, always the same. Try direct substitution. Because if I use direct substitution and it works, I don't get a 0 in the denominator, then I am done. And if I do get a 0 in the denominator, it sometimes gives me some information. All right, let's take a look. plug in the 4. Plug it in on the bottom. 4 plus 5 is 9. Square root of 9 is 3. I get 0 over 0. Okay, so we weren't allowed to use direct substitution. The difficulty here is because I don't have a polynomial, I can't just factor the numerator. So this is a case where I feel a little bit stuck. And the way to proceed here is a little bit less clear. So I'm going to remind you of an algebra technique. I'm first going to show you something that doesn't work. Okay. Suppose I start with the fraction 2/5. And I say, is that the same as 2 squared over 5 squared? Is 2/5 equal to 4/25? Well, 2/5 is 0.4. 4/25 is 0.16. So these are not equal. And this is the step where they're not equal. If I have a fraction and I square the numerator and denominator, I don't have the same fraction. I have changed the fraction. So we never want to square the numerator and denominator of a fraction to try and get rid of a square root, because I'll get a different fraction. In this case, squaring the numerator wouldn't even get rid of my square root, because if I square the whole numerator and I FOIL it out, I'll still have a square root involved. Okay, so don't square the numerator and denominator. Okay, we do have a technique that will get rid of that square root. If I started with a thing, right, the square root, I'll just call it an a, and then minus something else, right, I'll call it b, okay, and I want to square the a and square the b, right, one or the other or both, then if I multiply by a plus b on top and bottom, then if I FOIL out the numerator, a times a is a squared, then I have plus ab, negative b times a is minus ab, and the negative b times positive b is minus b squared. So I'll have a squared minus b squared. This actually looks like a problem that we had earlier, except backwards. Before, when we had the difference of squares, we factored it into what are called the conjugates, okay, so that we could cancel them. What we're going to do here is go the other way around. I'm going to multiply by this conjugate on top and bottom in order to get rid of the square root. Okay, so if I start with the limit as x approaches 4 of the square root of x plus 5 minus 3 all over x minus 4, I'm going to multiply by the square root of x plus 5 plus 3 over the square root of x plus 5 plus 3. And my goal is that I'm going to get rid of the square root in the numerator. Now, the denominator, when I tried to plug in, I know I get a 0. So I know I want to cancel this x minus 4 factor. So I don't want to do anything to that x minus 4 factor. I don't want to multiply out the bottom, because then I won't be able to see that factor anymore. So we're going to leave the denominator alone. So don't FOIL out or multiply out the denominator. Okay, so what I'm going to have now with my new limit, the square root of x plus 5 times the square root of x plus 5 is just x plus 5. Then I'm going to have plus 3 of those square roots, minus 3 of those square roots, so they go away, right? That's the whole point of multiplying by the conjugate. I don't get those middle terms. And then I'll have negative 3 times positive 3, and that's negative 9. Okay, so we don't multiply out the denominator. I'm going to continue simplifying the numerator a little bit. So plus 5 minus 9 gives me a minus 4. And now I have this nice x minus 4 factor in the numerator and in the denominator. Cancel them away. So we just have the limit as x approaches 4 of 1 over the square root of x plus 5 plus 3. Now use direct substitution. And we get 1 over the square root of 4 plus 5 plus 3. 4 plus 5 is 9. Square root of 9 is 3. So we get 1/6. All right. Okay, let's look at what happens if the techniques that we've studied up to this point don't work. In particular, if I have something like trig functions, I run into a problem. So what we're going to look at is this thing called the squeeze theorem that is a powerful tool that allows us to look at more limits, but it's not a very elegant tool. It can be very difficult to work with. So this isn't something that we're going to start a problem with. It's not going to replace our other techniques. This is sort of a last resort. When the other techniques don't work, maybe this will. And then in some cases, it's going to be essential. Okay, so let's look at a rough idea of how this works. Let's suppose I have a function, g of x. And let's suppose that this is a really bad function. Okay, and I mean that in the sense that I can't easily work with it. I can't factor it nicely, and direct substitution doesn't work, and things just break down. Let's suppose that it's stuck in between two functions that are nicer. Right, suppose f and h are nice functions. My bad function is squeezed or sandwiched in between them. Okay, if h and f meet at a, and they don't have to hit here, I could have a hole in the graph. But if they meet at this point, then the bad function is kind of forced to go to that point also because it's squeezed in between them. Okay? So it can do all of its crazy moving around and unpredictability, but if it's stuck between two things that come together, then it gets forced into that point. That's the idea of the squeeze theorem. So this is what the squeeze theorem looks like written out. Suppose I have these three functions, f, g, and h. They're all defined for x's near a, where my g function is squeezed in between the f and the h function. If the limit as x approaches a of f and the limit as x approaches a of h are equal to each other, which is the situation we were talking about, right? At this point a, the limits meet, then that's the limit of the g function also. That's what the squeeze theorem says. Okay, so let's look at an example of how to actually use this. If I look at this as a limit problem and I say try to plug in, try direct substitution, okay, plug in 0 for x, I'm going to get 0 squared times the sine of 1 over 0. And I can see I have a 0 in the denominator, so I'm not allowed to plug in, but it's inside the trig function. So, there's no factoring I can do. I can't factor things in and out of a trig function. So there's not really anything I can do here, right, algebraically, right? So direct substitution won't work. And we don't have any algebra things that'll work. There's no identities that'll deal with a 1 over x inside my trig function. Okay, so that means that this is a bad function. This is going to be like my g function. Okay, so think of x squared times sine 1 over x as the g of x. Okay, what I need to do is find an f and an h function, a function above it and below it. Okay. So we need to come up with f of x and h of x. And that's not always very easy. So here's how we go about this. I'm going to start with saying sine of 1 over x, sine of any number that you can think of, is always going to be between 1 and negative 1. So what I can do is leverage that. I now have at least the bad part of what I'm working with squeezed in between two things. So let's multiply through by x squared. So negative x squared is in between, oops, I forgot my x squared, is in between x squared times sine 1 over x and x squared, right? Multiply through by x squared, and now I have my bad function squeezed in between two other functions. Okay, that's the situation that we have here. So now let's see if these two meet as x approaches 0. So I look at the limit as x approaches 0 of negative x squared. That's 0. I'm going to look at the limit as x approaches 0 of positive x squared. Direct substitution, I get 0. These match. So by the squeeze theorem, the limit as x approaches 0 of x squared sine 1 over x is 0 also. Okay, so the squeeze theorem just gives me the result as long as I have met its conditions. Okay, that's how all theorems work. It's just this one is a little bit more confusing looking than some of the others. Okay, and again, this is kind of a last resort. We won't use this for a lot of regular problems.